It's a pleasure to introduce our next speaker, Ben Recht at Berkeley. He's been thinking a fair bit about RL from a controls perspective. So,
thanks, Shyam. Thanks, everybody, for coming. All right, so we're going to talk about, I was just speaking with Mariam that I've been editing my title over the last week. I've also been editing my slides over the last week. I may have changed a couple things based on Mangdi's talk. We'll see how it goes. So I guess the disclaimer here is this talk is really brand new. You guys are, it's a nice small crowd, although I guess the internet's out there. It's a mostly small crowd. But yeah, this is really new. It's something I'm pretty excited about. And I apologize in advance that it will probably be a train wreck accordingly, just because I haven't quite got my thoughts together. But anyway, this is a workshop, right? So let's workshop some new material. And this is the outcome of some really cool stuff we've been doing for quite some time, but really kind of a revisiting of some of our views on understanding learning and control over the last, I'd say, 6 months or so, primarily driven by all these folks. And in particular, kind of a heroic effort by Vicky Yi and Rohan Sinha to get some of these demos working, which there will be demos in the talk eventually. So, all right, so reinforcement learning. So obviously, everybody has been very excited about reinforcement learning over the past decade or so. I was just talking to Yishai about, we kind of got tired of it. I've talked to Chaba about this too. We got tired of it for a while, and then all of a sudden, machine learning got re-excited about reinforcement learning. And I'd argue part of the reason why is everybody always shows these two pictures, right? One of the reasons why is Go. That seemed exciting, and the other one is that people have started to do cool stuff where you're integrating, doing control actions directly from pixels. And in some sense, even the Go thing is sort of from pixels because you pixelize the board, and that's your representation. Right? So the idea is you have this very high-dimensional representation, and then you figure out how to act from that representation. And of course, some of the things everybody here is interested in is if you're going to put this in a car or in a warehouse or in some power grid, we need these kind of tools that map high-dimensional representations into actions to be reliable and to be trustable. So the question is actually, how do we get at that? And this led my group and I down a very deep rabbit hole. Because when you start to look at what people have done and try to generalize from the initial prototypes, it became a little bit difficult to figure out exactly where the salient bits were. So in particular, every time we looked into reinforcement learning, in practice, we found flakiness. So sorry, this is not the polemic. Come on, I can't give a talk without some polemics. Here's the polemics. OK, actually, there's lots of polemics. OK, so first thing we observed, most of these demos strongly depend on the random seed, which means they can't be robust and reliable. You change the random seed, everything breaks. Hopefully, everybody's seen that by now. Anyway, it's crazy. And hence, the experiments get to be very unreproducible. The sample complexities of models that go directly from pixels to action or from high dimension to action are I would argue, not practical. Mangdi pointed out that we had this thing that would be exponential in your state space if you take some of the current theoretical, what we've all kind of agreed on in terms of tabular spaces. And if you actually run a lot of these algorithms in practice, they do take a very, very long time to converge to anything reasonable. And I gotta say, once you start digging into it, the number of compelling demos is very small outside of video games. The number of things where actually people make this work, I think the most notable exception is like Jan Peters has been doing cool stuff with policy gradient and robots for 20 years now. And that stuff is really cool, but it's like you have to really look hard to find good examples of people using reinforcement learning, especially with high-dimensional sensing. And this is my other big problem, is a lot of times what is claimed to be solved and what's actually solved are very far apart from each other. And you have to dig into the actual code to actually see what's happening under the hood. So it's a bit of it's complicated. Look, here's what we came away from. Here's where I want to step back and come away from. I think a lot of good work came out of trying to unpack these things, and a lot of people here have done really interesting stuff in that space. I think a lot of, certainly I learned a lot by studying these problems. But at the end of the day, I'm not sure that any of the stuff that we've done so far actually gets us towards the problem that people were initially excited about solving. Let me actually skip this. See, this is where we're wood chopping. I'm just going to go ahead here. What's the thing I think people were excited about solving? Does that work? Yes. The thing people were excited about solving was trying to do actions from pixels. This was the thing that everybody kind of like initially captured people's imagination. This kind of gave rise to a bunch of stuff at OpenAI. Every time I've got to DeepMind from the practical side of things, not from the foundations team, and I have one set of conversations. The conversations I've had with people outside of the foundations team at DeepMind, they all want general purpose algorithms that work from pixels. I'm just getting a look from Chava now. And so what do I mean? I mean, the idea is that you have some representation on a grid, Space Invaders or kind of like actual pixels, right? Going in lower to higher dimensional from left to right here. And you want to get policies that map pixels to actions, right? And the question is, there should be a question mark, is there a reasonable approach to do control when you have, let's not even say pixels, but perceptual sensors? Sensors that are high dimensional, sensors that give us a lot of information, sensors that somehow are supposed to be mimicking the sensing modalities of people or at least animals. Okay. Right? So this would be audio, this would be vision. So how exactly do we do control or combine machine learning and control in some nice way to incorporate that kind of sensing modality? So cameras are super interesting, right? Cameras are super interesting because you are getting megapixels, so you are getting millions of time series per second, probably even more than that, which is simultaneously too much information and possibly too little information at the same time. And the question is, how do we actually make sense of that? And one thing I just want to start with, again, one more polemic slide, is the question is, I think my biggest beef is that every time you go and read a paper on deep reinforcement learning, the first thing they talk about is Markov decision processes. But at the end of the day, if I have a million-dimensional state space or a multi-million-dimensional state space, is it really worth modeling that as an MDP? Right? Or is it a POMDP? Right? That's the question. Is it an MDP or is it a POMDP? So first of all, do we need sophisticated learning in MDPs? The answer seems to be no. Right? At the end of the day, even optimal algorithms at the end of the day seem to be, let's estimate, if we have a small MDP, the best thing to do is estimate the model and then run some form of dynamic programming on top of that. So, no? Oh, actually, now I want to know. You agree or disagree with that?
You just killed all the model-free algorithm in one shot.
I mean, there are model-free. As far as I can tell, the current state of model-free algorithms is they're either provably less efficient than model-based ones in certain regimes, or in the regimes where they're the same, they're never better. Like we don't really have an example where they're better, at least in terms of sample complexity. You can make arguments in terms of other things, in terms of space, in terms of memory, but in terms of sample complexity, there's no regime where they're better.
Speaking, they haven't proven it, but there are isolated cases.
But I want it proven. In theory, is there anything? No. Okay. Yeah. Huh?
They don't converge to the same place.
Model free and model based?
With misspecification.
Oh, with misspecification, yeah. But here's just like nice, well-specified MDPs. Okay. Now, the second question was on that previous one, is pixel-based control best modeled by MDPs? And I'm going to say no. I think a high-dimensional state, even in classical controls, is problematic. This is why people spend so much time on model reduction. Having a very high-dimensional state space is hard because everything scales badly with respect to state dimension. So if you always want to reduce to low-dimensional things, and the bottom line is if you are trying to do something like move an object through space, the actual state that matters is very low-dimensional. It is not megapixels. Yeah?
I'm confused about the question that you're asking here.
Yeah.
Everybody question about Markov state or?
Good question. Yeah. Yeah, that's great. That's great. So I'm going to try to make this clearer in the second half of the talk about what I mean. Well, actually, even in the first half of the talk, what I mean by POMDP versus MDP. But I mean in the most naive version of it, the most naive version of a hidden Markov model, right? In the most naive version, you have a Markov property. Let's just leave that be. The question is, am I observing the state, or am I observing some other representation of the state?
To me, if you're observing something that is a function of the state but has a state Markov property, the same way as like the reduced reduced state, then like it's still an MDP. It's fine. It's just like there is some additional difficulty because you don't have a reduced model in your hands.
You don't have a what model?
Reduced, like your model is overblown. right?
Yeah, so but that's part of the issue. Again, so I guess the question is,
But MDP.
let's see how I say
To do that.
it's about modeling, right? It's just about modeling. So would you rather model it as the Markov property in high dimensions, or model it as a high-dimensional observation of a low-dimensional Markov chain? And that's the question. I'm asking about that actual. Do you want? Sorry.
I mean, still MDP, it's just a low-dimensional space.
Right.
Additional structure.
Yes.
You want
And
to
that's-
emphasize that? Okay.
Yeah, but that's still a POMDP, right? The actual model where I have an observation of a low-dimensional.
Specific POMDP doesn't have a lot
Fine.
of
It's a
problems.
specific POMDP.
Yeah.
No, why you say no, Al?
No, because partially observable means a technical thing, right? And so if you are thinking about the observation as being sufficiently descriptive, then we would be misleading ourselves by calling it a POMDP.
I see. This is what I disagree with. This is what I disagree with. I think partially POMDP is a model.
This
It's
is
not
nothing
a
new
state
in
of
the
mind.
last like 20 years, right? Like if you go back 20 years and we talk about function approximation, we know that function approximation MDPs look like POMDPs.
There you go.
So it's not like this perspective is any.
Well, but I just asked the question: should we model it with MDPs? And I think the answer is no. Why not? Well, the reason why I say why not is because
But this isn't a new perspective.
it convinces you that you're observing the state.
No, so the reason then that this is different is exactly Alex's point. That as your function approximation gets better, information theoretically, there's a reason to believe you don't need uncertainty, whereas in a POMDP, information theoretically, you actually have to keep around historical information to control your system.
You have to take actions
That's a
to
real
figure the
difference.
state. To you or not? That's a POMDP. If you have to take actions to just figure the state or figure the reward, that's like, wow.
Yeah.
That's a very different model.
Yeah. So that's the question. So actually, this is exactly the question.
Okay.
This is
That's
exactly
the
the question. This is exactly the question because MDP suggests that you don't have to and that you could directly act, right?
Yeah.
POMDP suggests that you have to do some kind of filtering. That's exactly right.
And that's exactly.
Oh, and that's the question.
But this is like known, right? This is an old perspective.
Of course, it's an old perspective, but I'm just telling you that every DeepRL paper I open, and thousands of them are written every day at Berkeley. We got 1,000 papers on DeepRL at Berkeley every day. They all tell you about MDPs. They never even say POMDP, right? And they're different problems. You agree they're different problems.
I absolutely agree that there are different problems. I think that these guys mean that you stack a few frames of the video and you effectively have state information in your hand. And then there is a secondary question, is that still a problem because your state representation is overblown?
That's right. That's right. So there's two issues.
different.
Well, there's two issues, right? There's one, the overblown state, which also means modeling it as a POMDP is useful, even if the filtering step is simple.
Okay.
But the second one is, as Chava is pointing out, the real question is, do I actually have, from a few frames, a representation of state always? That's also not clear. So there's two issues. Good. That's good. Oh, this is another one. This really makes us really angry. Is additivity and regret the right framework? I think here the answer is kind of sort of, but I think, Monty talked about this, we all kind of talked about this. At the end of the day, most of the tasks that you see people do, and again, all of this stuff right here, Sean, it's not about theory. It's about what questions should we be focusing on if we want to actually understand what people have been doing in practice, right? Because like you said, theorists have thought about all aspects of these different parts of this table before. I just want to know which ones should the theorists be thinking about that are best representative of what people are trying to do in the control from pixel space, not in general RL, right? And this in particular, the one big thing that is kind of, it's always weird. Like people talk about exploration, people talk about interacting with the environment, and then you see every single demonstration, and I repeat the same task a million times. And those are different. So almost everything in implementation is episodic. Actually, everything in implementation is episodic. Meaning you get to repeat and repeat and repeat over a fixed time horizon until you're happy with the performance. And that's very different than a kind of regret framework, which you get one go, and if you crash, you're in trouble. How? Oh, yeah, fine. We could. People do that. But at that point, it ends up being like optimization, right? I mean, regret and optimization look very nice, similar at that point.
It's a big bandit.
It's what?
It's a big bandit.
It's a giant bandit. Yes, yeah. It's a giant. We could do that. All right. So there's my three no's for you guys. Yeah.
Are you going to fold somewhere in this argument the notion that often rewards and everything, like even state information is delayed and you're acting on state.
So this always comes up when I talk about reinforcement learning, and this is a good question. And I never understand that question. I never understand the question. The question of delayed rewards, the question of, I'm not going to talk about it. I just don't think I don't think those problems are real either. The delayed reward,
So it's
we
not
could
part
invent
of any
them.
question you're raising.
No, I think the task is well defined. Let's just say the task is well defined, because otherwise things get complicated. Yeah, what?
No, I was just reacting to what is the same thing as control people talking about how frequently you're sampling your system, are you fast enough? I think that's kind of the same thing. Like, if you need a very fast controller and you're sampling at a very low rate, you will have trouble with
Yeah.
not.
You think that's an
I think
interesting
that a
thing.
lot of
But
times the delayed reward is related.
Whenever I see delayed reward, it's like you get 0 reward until you get to the end of the maze.
That's the other meaning of delayed.
Okay, so which one do you mean?
The observations are delayed. Even if you're sampling fast enough, if things are getting buffered and you're getting your observation 5 seconds after,
Yeah.
you acted on past information and you might take a bounce back.
I'm not going to talk about that today. But maybe that's something we can talk. Delays make everything hard, so that's fine. I'm going to try to minimize some of the complexity. What am I going to talk about? I want to talk about iterative vertical control from high-dimensional sensors using as little machine learning as possible. That's what I want to talk about today. Let's just see if that's possible. Let me motivate this. Let me give you an example. I have a quad rotor. Hopefully if anybody's seen my talk before, I always use this quad rotor. I love that guy. And this quad rotor, you want to move it, right? And so the control problem at the end of the day is actually I know the dynamics of the stupid quad rotor. At the end of the day, I can weigh it, and it gets to fly in free space, and it's pretty simple. And if you want to make it even more complicated, I could put on the actual dynamics of the propellers, and it's not so hard. It's a very well-specified model. And hence, if I want to do optimal control, just for you, Shah, there you go, man. If I want to do optimal control, I could write this problem down, assuming I observe my state. If I observe my state, the problem is very simple. If I don't observe my state, and instead I'm going to try to fly this from a camera, which, by the way, this is not coming out as nice as it looked on my screen. Gorgeous picture taken by a drone of a castle in Ireland. Not by me. But anyway, I was just looking for drone photography is actually pretty exquisite. So if instead of observing the state, you observe the relative position based on me being up in the sky, I introduced a new problem here, where I have to at least invert this map H, and assume I can invert that map H noiselessly. Right? Noiselessly being the key, right? If I can noiselessly invert it, then I just have a normal MDP problem. If I have to learn a mapping that inverts it and there's uncertainty, all of a sudden now I have a POMDP problem. And this is, I think, maybe makes it a little bit clearer about what kind of that distinction I'm making. Right? Do you buy that, Sean? Right? If you invert it, I don't get perfect state representation back, because I go from image to state. Now I have a noisy measurement of state, and I have to filter. Yeah, okay. I could add that later. We'll add that later. I mean, you want to make my life harder. We could make everybody, I mean, this is the thing, right? This is about still really simple. But as soon as you add in this weird high-dimensional observation, a problem that goes from optimal control, it gets more complicated. It gets more complicated. Especially because usually perceptual sensors, the representation that we start with, this mapping, is almost always nonlinear. Maybe we can get some simple cases when it's linear, but most of the time that high-dimensional observation is nonlinear. So most of the stuff that we started to dig into, actually, how you would solve that problem. And there's great stuff out there, which I don't have time to fully go through, but like these websites all have really cool ideas, kind of inspired from very different perspectives of things. In particular, these are the 3 groups where I think I've learned the most for this project. I'm sure there are other people I'm forgetting. Okay, but in particular, Francesco Borelli, who actually has helped us a lot with this particular project. Is Byron here? Byron will be here. He's on the schedule. Has done really cool stuff at Georgia Tech. And Davide Scaramuzza at ETH has done probably combining this one and this one is probably the closest to how we kind of got to an understanding of how to make something work. And when I say how to make something work, so the one thing that Byron said to me last time I saw him was that now don't get mad at me, get mad at Byron. If you're writing papers about reinforcement learning or learning to control and you're not actually doing it on robots, then I don't believe anything you're saying to me. That's what Byron said to me. It was a challenge. So I was like, okay, let's go do some stuff. let's go do some stuff. And I have to say, the people who are most resistant to this are the graduate students who have all convinced themselves that if you touch a robot, it adds a year to your PhD. Every time you touch the robot. I don't think this is true. And actually, Rohan Sinha and Vicky Yee spent a summer putting this together, and it was only a summer. So hopefully, if they're watching on the live stream, they did great work. It wasn't a year. So this is a platform that was developed by Francesco's lab. This car has a camera. Well, we put the camera on there. That was this big thing. Actually, Aurelia Guy who's now at DeepMind, was kind of the first person to just add this extra camera jig to the car. The other sensor that this thing has is it has a little accelerometer to give you inertial measurement, and it has encoders on the wheels. And the question is, can we drive around a loop? This is our challenge. This is kind of our simplified problem. I'm going to give you a single demonstration of a loop, and you want to drive around that demonstration as fast as possible, staying close to the loop, but increasing your speed. Okay, so it's a fairly well-described thing, and the only sensor you get is camera, IMU, and encoders. Okay, so no global positioning. Yes, but I want to go as fast as I can around that single trajectory, or near the single trajectory, without crashing.
Trajectory tracking classic function.
It's not quite, right? Because again, it's
Yeah.
tube tracking, staying around a trajectory, but trying to find something that's better. Right? You want to stay nearby the. You'll see in a second why that matters. That'll be video. Okay, so this is what that camera sends back. This is in the Wozniak Lounge. Just give anyone over there. And so this is challenging for a couple of reasons. One, cameras don't have depth. Everybody knows. What single camera? You need two to get depth. And all the coordinates here actually end up being relative, which actually makes it a bit tricky. So the question is how to do that. Then there's no track. We have multiple coordinates. So this is a solution. It's not the solution. Actually, everything here is just a solution. But I want to talk through how we did it and where the layers of abstraction happen. So lap 1, the human just gives a demonstration. Using only the data from that first lap, we build a map using the images. And the algorithm we use is called OrbSlam, which is just probably the most state-of-the-art version of SLAM. The reason why people like OrbSlam is because it can run in real time, which is important because we want to drive around the car. In some sense, it's a little crazy to try. I mean, I don't think that people do, like if they're running around a track, are using their visual sensor for positioning. But anyway, so it's, whatever we're doing here, we're going to try to do control action from the images itself, right? We're going to try to do driving from pixels. Okay, so immediately after that first lap, we have to calibrate what the encoders are telling us with the images. I just put that on there. Lap 2 to 3, we just trace around the trajectory using a PID controller to get a few extra estimates of what's safe and nearby. And kind of we have this special parameter saying how far we let the car deviate. That's one thing that was a parameter that's encoded. And then lap 3 to 30, we improve the performance using what's called Learning MPC. That was developed by Ugo Rossolia and Francesco Borelli. Okay, so let's walk through these just in case you haven't seen it. Who hasn't seen SLAM before? Oh, cool, good. Okay, no neural nets. There are no neural nets here yet. We'll add some later, but yeah. So but I think it's deep, right? Because there's like multiple parts. So, okay, right there. So here's SLAM. This is this is a dumb project, but I actually had taught myself a bunch of computer vision by trying to do visual analysis of football game tape. This is from 5 years ago. I find this useful because it's very easy for me to explain to you SLAM using this picture. So this is a single frame from a football game, and I want to build like a panorama, kind of stitching out a map of the full field from a video of a football game. So the first thing you do is you find these things that are called key points or corners. And there's an algorithm to do that, but essentially it's places where the gradient norm is very large. Okay, and so and then what you have to do is make sure that your key points are spread out. That's the first step in any of these algorithms. I look at an image and I try to spread it with things that look like corners. Okay, and so these are the things that look kind of salient like corners. Then if I have two adjacent images, I take those corners and try to compare them to each other. So I look for all correspondences between all corners. And then I take the ones that I think are good. Good, it turns out, is if the first nearest neighbor is significantly closer than the second nearest neighbor, we call it good. That's an amazing heuristic in here that I can't back propagate through. But anyway, there we go. And now I get correspondences. And once I have these correspondences, now I actually can just compute. If I know they all happen in the same position, I could compute a geometric transformation to put them in the same coordinate system. This allows you to make these beautiful panoramas of like, I don't actually have the panorama here. Just here's another example I pulled off the web. You kind of get these things. This allows you to stitch together panoramas. Google does this automatically for you when you take pictures and you go to some beautiful place. And this is the whole algorithm behind it. But you can imagine it also gives you these, if I have all of these transformations, I can now just construct the actual 3D geometry from a bunch of two-dimensional images. So that's SLAM. We do that with the first lap only. Iterative MPC is a really cool idea that we throw in here. Actually, I want to kind of ask the peanut gallery here if this is machine learning or not. I don't know. So this is standard MPC, where I plan based on a finite time horizon version of some infinite time horizon problem, and I approximate the Q function with a terminal Q function. Okay, and so every time I run this optimization, and then I get a new x0, and I run the optimization again. Right? This is model predictive control. Iterative model predictive control is an incredibly clever idea that kind of combines ideas from Q-learning with MPC. And so the idea here is we're going to learn the terminal condition. And it's very different from kind of the algorithms that we see in kind of the more bandit version of Q-learning analysis, because in there you try to explore places you haven't been, explore places with high uncertainty. Here, we are constraining the file stat, like the place you have to go, to be a place you've seen before. And then the Q is just what was the best value we've ever seen at that point. And so if you ever go again and you get a better value, because again, it's episodic, we're going around a track, you get a better value, you would update this value here. And then you're always updating the set of possible places to go here. Okay. And what's fun is, so where's the exploration? Right? This doesn't seem to be able to explore because we took away being able to go to uncertain sets, except that there's no constraint over where it goes over here. I give myself n steps to explore, possibly to get to that last thing with higher reward.
So you assume that R is known?
R is known. That's not what the question was at the beginning, but yes, I assume that R was known. Actually, for racing, R is really simple. R is T. You get, essentially, you want to minimize T, so you're going to pay 1 if you're not over the finish line, and you're going to pay 0 if you are. And you just want to minimize T. Right? So it's kind of, that one's pretty cute. So if you could get to a state, like again, if your final state is over the finish line, you would pay 0 cost. So that's a good place to try to get to. You try to get there as quickly as possible. So R is known, the dynamics are given, and then we say stay near the demonstration and put limits on what the control values are. And that's the thing you solve at Irish.
E is noise?
Yeah, E is some kind of noise, which is modeled or unmodeled in that one. Yeah. Okay. All right. So again, is that I don't know if I call this machine learning. I don't know what to call this. Chava doesn't know what to call it either. You guys think? You guys tell me later. Okay. Okay. And here's where actually the learning comes in, because it turns out you could write down the model for the car. You could write down all the dynamics, and they're very well specified, except that you have these. So you have the yaw angle and the relative XY positions, so everything is really nice. The one problem is that you have these weird parameters that depend on the axles of the car, and you have these other parameters that depend on the contact between the tire and your particular surface. And so actually characterizing those you could do, but what Ugo did in his PhD thesis, which I think is nice, is just fits local. It's such a, this is machine learning. Remember, we're storing all the places we visited in the low-dimensional space. We just look for recent places, recent times we've been in the same spot, and fit a local dynamical model there. And so this actually allows you to push. So what happens here is that at low velocity, at low velocities, you end up being in this linear regime for friction. The faster you go, the dynamics change. And this allows you to adjust to the dynamics changing based on keeping a running history. And then this one we use. We actually linearize it because it makes our life easier. But we do use these, which I guess we call kinematic models. This is just a mapping from local to global coordinates. But we actually fit all the stuff that involves forces using LTV. So that's machine learning. That counts. And that's about the only machine learning. Oh, now there's a demo. This is great. This is great. So this is what Vicky took this footage on Friday. So it's always just in time for the workshop. So this is the demo that she input. She's driving it right now. The thing is that in order to drive it, the way she drives it is she has to look at her screen and not hit things. So it's actually a little awkward. She's not looking at the car, she's looking at the screen, which is it's doable. I think for people who play a lot of racing games, Gran Turismo fans would be good at this. Okay, so now here's the key points that I was talking about in the slam. That happens here. That's our first round. You see they're all over the place, and there are lots of them in the carpet that are kind of flickery. We don't want those. Okay, and then again, now you go, this part's actually really boring. We'll let it play. This is the most boring part. It has to get that, in order to get safe states, you need that PID controller to go around a couple times just to figure out, get a good region of what things are safe.
What's the state PIDs? Like, what's the observation PID observation?
So this is also a great question. So it's something I probably should emphasize more. We're doing certainty equivalence, which I don't think we should be doing here. And at the end, we're going to talk about why that's a bad idea. Maybe, although I'm going to be out of time. So probably not. But what we're doing is we're taking the output of the SLAM with the IMU and then running it through a state estimator, an extended Kalman filter, and then taking the output of the Kalman filter as the state. So it's a certainty equivalent controller. And then at that point, it's low dimensional, right? Yeah. All right, where are we now? Is it improving? Still not doing anything. It starts to get better.
What's the green stuff?
The green stuff is where it's hoping to go, right? That's the planned trajectory from MPC. Right? MPC has this horizon. It's where it thinks it's going to go. And then it gets feedback at every time step. All right, eventually it's going to be cooking. Come on, car. I should have edited this better, but that's okay. You got to believe in our race car here. Huh? It's getting faster. It's getting faster. What you also see is it's moving away from the trajectory a bit. This is actually important. Improve. All right, this is a fast one. What I think is really interesting is it starts to find an oval shape, which is actually what it should find, because that would be optimal. It's not there yet. It moves away from the track to find something oval. Come on. There we go. 20 laps. Now it's going okay. And now you actually, if you see the blue down there, it has actually converged to an oval trajectory. Nice. That's much harder to drive. Oh yeah, is this happening now? So do you see how the green points go off? So that's the other thing that I think is really interesting. At this speed, the vision is failing.
Delay.
I don't know if that's delay or just sensor error. Actually, I don't know what you would count that as. Delay or sensor. Yeah. So essentially, when we don't get it, the Kalman filter just propagates forward without that information, which is probably a better thing to do. Just I could do that in a second. The other thing is it does work in other rooms, which is also kind of nice. Different room. I'm only going to show that quickly. Here it's going around chairs instead of going around a rope. So you could kind of with one demonstration with various kinds of clutter, it actually seems to be able to, it seems to be somewhat reproducible. Yeah, Dan, go ahead.
Something. The main feature that's keeping it slow at the beginning is that it has to end the look ahead at the same speed, at the speed it's gone at before.
Yeah. Yeah. So it has to keep increasing, right? So it has to end at the same trajectory that it's. But you see that
if you have a long look ahead, then it goes too fast.
So we're still trying to, again, this video is from Friday, so we're still trying to stress the test, and I think that's a great question. The biggest problem we have with a longer look ahead is real time. The longer you make it, the harder the computation is, and I think right now it's 8 steps or 12 steps, and it's and we're pushing up against the limits of what we can do. This is the speed improvement over time. Yeah, go ahead.
How do you transfer the knowledge of rows to chairs?
So we do in the new room. You do one path. It's the same thing.
Okay,
You always every time you have to do one initialization path, then it learns from there to go faster. And again, it always kind of ends up being the human by a few, because humans aren't that great. Okay. And maybe we can get rid of it. Actually, what's interesting is that everybody I've seen who has some kind of form of this, there's always some catch with how you actually define the initial track. So for example, Scaramuza has this thing where the quadrotors fly towards big orange beacons. So once you have, which we could do, you put big orange salient beacons in the room, and then it can actually interpolate between those. The Georgia Tech people have a real fixed dirt track that they're always using the same track. So there's always anyway, that's always going to be a little bit of conceit. You need a little bit of mapping, and the question is how much. A little bit of pre-mapping just to specify what the task is.
Big the safe set is.
Or they have to know at least something, for racing, they have to get some information about what the track is. But it's interesting, you can always get the track in local coordinates in all of these cases. Okay. Yeah. All right, so I want to just talk about how first of all, so we did use machine learning, right? So there was a little machine learning in here. How do we model this, right? So the big thing was that there's unknown locally linear dynamics. But in some sense, we've studied this. Right? This is the MDP problem. If you have full observation, this is just the MDP problem that all of us have been studying. So that's cool. Right? Well, come on. Or tabular dynamics. Which one do you want, Sham? Whichever one you want. It could be tabular dynamics or it could be linear dynamics. What are the two? Huh? Yeah, that's LQR. Yeah, but, right? Yes. I'm saying, we've already done this one. That's LQR. That's nice. But then we have this observation model in this higher dimensional space. Right, so it's just I add widgets to it. And now you have this observation model in this higher dimensional space. That's kind of messing our lives up. And the way we're modeling it, and I don't know if this is the right way to do it, but the way we model it is using perception as a virtual sensor. So meaning, and this was kind of the idea, this is how we think about it, and this is how we've been trying to analyze it, is that what we're going to try to do is take this high dimensional model, do something to it that now puts us in a framework where we'd actually be able to solve the normal control problem. Right? If I had x and y and no z, it's just ordinary linear control, maybe time varying, but ordinary linear control. And the question is, can we actually think about this mapping, and this is where kind of like the computer vision would come in, from observation to this virtual sensor, and think about how to actually include that in this control loop. Yeah, Isha.
Just to understand the notation. What is capital delta?
Okay, yeah, let's go through the delta. H is this function.
Mapping from
delta would be some kind of error in the lifting.
Okay.
So like it could be like
this
is state dependent and not state dependent. That's the way in the paper we did kind of distinguish those two. I could just lump it all together into state dependent. It doesn't matter.
What's statistical and what's not statistical here? So
it's whatever you want to be. So it could be worst case or statistical. I'm not pinning anything down. Yeah. No, exactly right. I mean, because I think both cases are interesting, right? So one would be the robust versus stochastic cases are both interesting for me. So W and V or N E. E is actually the one that's not statistical. This is the one that comes out of this. E is a function of V, delta, and this inverse map. So that one's just given. But the idea being that you're trying to map yourself back into a regime where you just have linear control. That's nonlinear control. And then the question is actually how do you handle that question? And you do want to do control design around it. Okay, so I'm basically out of time, so I'm not going to go through this in detail. But what we've been looking at least from the theoretical perspective, and if I had another 45 minutes, I guess I could tell you about this, is this kind of model where if I put myself into this setting, where I have linear dynamics and fixed linear cost with an error, this framework is just standard output feedback control, right? Yes? Sure, right? And so the question is, what we end up doing is modeling, let's see if I can do this. Yes. So you take a nonlinear observation process and turn this into a time-varying and state-dependent error process in output feedback. And that's been kind of the way we've been modeling it. So rather than try to go into that, let me just see something here. I'm just gonna skip ahead to What's interesting here is that even in this model, where if you think that that perception thing is coming from something control related, thinking about how generalization works is pretty interesting. I don't have time to go into the basis of this theorem other than to say that I just want to kind of just throw this up as an advertisement and nothing more, is that what we're able to show is that you can get robust performance, but you have to mitigate the interaction between this virtual sensor and what you actually do. So we have to control, in this case, if we can kind of control the effect of that error in that sensor and how that maps into the state, and we make that small during our control synthesis, we're actually able to do robust performance even if we have errors in our perception. So I apologize that we don't, I'm out of time, so I'm going to just skip to the end if I can figure that out. Let me just do this. All right. All right. So there's a lot to do. This was new. I obviously did not get through all the things I wanted to get through. I think that the main takeaway is that this idea of using a perception map and separating it out and using it kind of as a virtual sensor, I think has legs. It seems to work. It seems like a lot of other groups are doing it, and it kind of breaks this like end-to-end thing apart in an interesting way. What's also interesting, and again, I wish I had time to talk about this, but actually understanding how to do generalization in these feedback loops I think is pretty interesting, is a little bit simpler in this case than thinking about what, well, maybe it's the same problems in RL. Maybe it's exactly the same problems. Not simpler at all. I'm thinking about this to myself now. The problem is that if I collect data using a particular policy, in this case the PID controller or the human, and then I implement my controller using somebody else's, using something that I've designed, the perception map is now going to come to me, the data is now going to come to me with a different distribution.
It's enough policy.
What's off policy?
You're viewing a behavioral policy and you want another, to estimate another policy.
Yeah, that's all, yes, exactly. Exactly.
You're avoiding all the buzzwords for L.
I don't know, because I can never remember what they mean, man. I still don't understand the difference between model free and model based, so I got stuck there. Yeah, so I think that is probably the off policy versus on policy problem. But here we actually have, what's funny is that if you have the vision component, now we're combining this issue that you already have in reinforcement learning with this issue of generalization in that standard sense in machine learning, and they play together. And maybe, in this case, we actually have a way to control it in this very simple model. But I'm curious to see like what other things might be able to be brought to bear there. OK. Let me stop. That was a bit, like again, like I said, we're just starting to think about this. We're just starting to think about how to put this together. We do have a paper on trying to figure out how to do this, this generalization component, which I didn't really tell you about today. But I'd be happy to tell you about at this discussion section this afternoon. All right. Thanks.
Time for a couple of questions.
Actually, I missed that point that you had the nonlinear map H. Do you iteratively linearize H? Is it similar to like iterative algebra?
So no, we just use the nonlinear map. And in fact, for us, the SLAM map is very nonlinear. And it's very different than what you do in a neural network, which I think is kind of, it's even, in a lot of ways, from a understanding it perspective, it's worse. Because a lot of folks treat neural networks as if they're Lipschitz, which maybe is reasonable because it's a function from images to something, and it's just a straightforward function. In SLAM, you solve 4 optimization problems to get out your state. So to go from one image to an actual XY position requires solving 4 nested optimization problems. So it's a really weirdly nonlinear map to get back to that state estimation. Yeah, that's H. So yeah. So I don't know how to think about even what the right, in the theory, we think about everything in terms of how smooth the perception map is. As what we see in practice is that the map is not smooth. And in fact, the errors are not smooth. As like you can see the flicker. Flicker is not really well modeled. That's, I guess, maybe easy to model too, as, what would you call that? What's that called, the communication, where you just drop packets?
Erasure. Intermittent measurements or missing data?
Erasure. That's the word I wanted. I want erasure channel. Erasure. That's it. Thank you. So it's like an erasure channel. So that's probably a better model, which we haven't considered how to do that yet.
Question.
Yeah, so in your model, we had the reduced space. So when you go from the Z space to H of Z,
yeah,
you assume that it's linear with respect to x, so it's cx, so we have a normal.
Yeah, so actually, let me go back to that. I went by way too quickly. Okay, I can get there. Oh man, look at all this. I'm just showing you all the stuff we missed. Okay.
Yeah, it's here.
So this one I actually think, so we wanted to have the ability to not map back to x. Even if you map back to x, it's still a hard problem. Even if the perception map, P, maps back to x, if you have x plus noise, you have to filter, which is the thing I want to keep coming back to. It's not an MDP problem because I have to filter. But here we wanted to be able to map back to c times x. So the simplest example, we map back to an estimate of position, not an estimate of velocity. Right? So c is now an estimate of position, not an estimate of velocity. That's the simplest example, and that kind of allows us to have that interpretation. It's just saying we're mapping back to some linear function of the state.
Let's do one more question.
Go ahead.
Can you talk a little bit more about the planner? How much horizon was important? Can you keep it short? Can you fill out multiple samples?
So
What was important there?
we were trying to do real time, and which was kind of like that last lap, which was those last laps were fairly fast. Our biggest limitation for setting the time horizon larger is just computation.
And how long is this right now?
That's a great question because there's latency. I can get that number to you. Let me get that number to you. Like it's this kind of thing where with software engineering, I'm sure we can make that part faster. But now we have this problem that I don't even know if this is the right solution. So should we do more software engineering? And that's like
That's why I was asking.
Yeah.
There's a trade-off between these two. How much you want to shoot versus how many samples you want to get.
Yeah, exactly. Well, but it's also this trade-off between if this isn't the right solution, I don't want to necessarily throw more cycles at it. You know what I mean? Meaning that maybe there's a better thing to do, and we're still not quite sure. Yeah.
Let's just do the questions offline. Let's thank Ben again.
You and me, man, right now.